In this video, I'm going to inspect two case studies regarding this equation, the equation that describes mu3. First, what happens when sigma 1 squared approaches infinity, and second, what happens when sigma 1 squared approaches 0. So let's start with the first. What happens when sigma 1 squared approaches infinity? It means that mu1, the prior estimation, is very inaccurate. Therefore, in the posterior process, we should favor mu2. We should favor the measurement we are getting from the sensors. Therefore, mu3, the new posterior mean, should be closer to mu2. So if we are doing the math, so we try to compute the limit of this equation when sigma 1 squared approaches infinity, what we will get is the following thing. I'm going to eliminate sigma 2 squared because sigma 2 squared is much smaller than sigma 1 squared, and then I'm going to eliminate this one. Again, sigma 2 squared is much smaller than sigma 1 squared, and then I can cancel sigma 1 squared and get mu2, which is exactly what we said in the beginning. When sigma 1 squared approaches infinity, it means that mu1 is very inaccurate. Therefore, we should favor mu2, the measurement or the mean measurement we are getting from the sensor. Now let's go the other way around. What happens when sigma 1 squared approaches 0? What does it mean? That the prior distribution, mu1, is very accurate. In fact, it is much more accurate than the measurement we are getting from the sensors. Therefore, what do we need to do? We need to favor it, and mu3 should be closer to mu1. So if, again, I'm going to compute the limit of this equation, but this time when sigma 1 squared approaches 0, so I will cancel this one, and I will cancel this one, and then I will cancel sigma 2 squared with sigma 2 squared, and I end with sigma 1, which is exactly what we said at the beginning. So again, these equations let us see that the Kalman filter is basically a weighted average between the prior distribution or the prior estimate and the measurement we are getting from the sensors. And we are going to evaluate or weight each distribution according to its sigma. This is basically what the Kalman gain does. And the most fun thing about the Kalman gain is that we don't need to compute it directly. The process of the Kalman equations is doing the things for us.